All right, if you're on Zoom and you haven't already done so, please let me know that you are here. Today we've got a bit of material to cover, so we're going to go ahead and jump right on in here. So we are beginning chapter 5, which is bipolar junction transistor amplifier circuits in earnest today, excuse me. So let's start with some basics. All right, so you guys, or at least those of you that took me for ELEN 223, may recall our basic fundamental definition of an amplifier. So just as a quick refresher, from a black box perspective, any amplifier circuit looks like this. Here. So just to be clear about what I'm talking about, this stuff over here to the left would be considered our source. This stuff over here to the right would be considered our load. And here in the middle, we have our generic amplifier circuit. Okay. Now, the amplifier circuit is not simply made up of two resistors and a dependent source. We can represent the amplifier circuit, no matter how complex it is, by this representation, which is defined by those three parameters, right? So the big things of interest in this representation are the input resistance Rn, the output resistance Rout, and the voltage gain AV. If we know those three things for any amplifier, we can greatly simplify our analysis, okay? So we have a lot of prior experience calculating the voltage gain of amplifier circuits. We're going to do that an awful lot with op-amps way back in ELEN 223. You probably did it even more so in ELEN 224. We've done it a few times here in ELEN 335, so I'm not going to focus on that too terribly much right now. What we're going to be talking about today is largely how to determine the input impedance and the output impedance of BJT circuits. So we are going to develop a methodology for measuring input and output impedance to start off. So let's begin with measuring input impedance. All right. So for a generic two-port amplifier circuit, doesn't matter what kind of amplifier circuit it is. I'm just going to call this a black box amplifier circuit. We have input terminals, which I'm drawing on the left-hand side, and output terminals that I'm drawing on the right-hand side. If we wanted to determine the input impedance, what we would do is we would apply some test voltage to the input terminals. I'm going to call this guy Vx. And just in case there was we were using a practical voltage source, I'm going to define it very specifically. Our input resistance is simply defined as the ratio of Vx, the voltage drop over the input terminals that are connected to our source, divided by Ix, which is the current flowing into that terminal pair. I want to point out here something very important. The output or load terminals are open circuited. We do this because if we see the load effectively in parallel with the amplifier circuit, we are going to see the loading effects of that load included, which is not characteristic of the amplifier itself. So we need to make sure that we disconnect that load whenever we're trying to determine the input impedance of an amplifier circuit. Now for us, we have BJT amplifier circuits. So it might be more useful to define the input impedance as it applies to a particular terminal, as opposed to a pair of nodes like we have here. So I'm going to draw 3 different common Bjt Op-Amp topologies, and you guys tell me which one you want us to find the input impedance of. So let's start with this guy. So this is the one we've done a lot to this point. This is what's called a common collector amplifier. Then we have a variation. This guy is a common collector amplifier, also known as an emitter follower. And then our third option for a Bjt amplifier circuit, let me make sure I don't draw this incorrectly. RC VB, and here is VCC. This guy is a common base. So let's talk about this terminology just real quick so that we're all on the same page here. Okay, so a common emitter amplifier is any Bjt amplifier in which the input is applied at the base and the output is collected at the collector or sensed at the collector. So common emitter. So the emitter isn't used for the input or the output signal, so it's common to both, which is why it's called a common emitter amplifier. For the common collector, the input is on the base, the output is on the emitter. So the collector is a common voltage to both of those signals. So that's why it's called a common collector. And lastly, we have the common base, where the input is applied at the emitter, the output is taken at the collector, and the base voltage is some fixed voltage that's biasing this thing in the forward active region. So which of these three guys do you want to take or learn how to take the input impedance of? Just pick one.
Go in order, I guess.
We're not going to do all of them because they'll take all damn day. What do you say, Dasha? Common collector. All right. So let's look at the common collector and how we're going to take the input impedance of that. So let me find my notes. Do you want to do it with the early effect or without the early effect? With. All right. Common collector with the early effect. So in order to take the input impedance of our common collector amplifier, we need to recognize one very important thing, and that is BJT amplifiers are small signal amplifiers, which means we're going to base all of our parameters for the amplification off of the small signal model. So for a common collector amplifier, with the early effect present, let's start with our small signal model. So here is base. Here is our resistance R pi. Here is our voltage V pi. Over here, we have our current source, GM V pi. In parallel with that, because the early effect is not being neglected, we have some resistance R naught. Here is our collector terminal. Here is our emitter. All right, so for the common collector, there is a resistor placed between the emitter terminal and ground. So that's this guy right here. The input signal is applied at the base, and it's a voltage between the base and ground. So here is our input signal, and this is going to be our test voltage, in this case Vx, and we're trying to determine that current Ix so that if we take the ratio of those two guys, we have the excuse me, input resistance. Now, the output voltage is the drop over this resistor RE. So I need to make sure that there's effectively an open circuit terminal pair here at our output, which is perfectly fine. Our collector, large signal is at VCC, which means small signal, it should be grounded. So that means we need to short the collector terminal to ground. So this is our circuit by which we're going to determine the input resistance. The ratio of Vx divided by Ix will give us our input resistance. Now, this representation of the circuit, to me, is a bit ugly and unmanageable. It's not remotely intuitively obvious how we would approach this. So I'm going to redraw this circuit slightly. So let's say this was the base. This guy down here, connected to ground, is the collector. And then let's put this guy right here as the emitter. So between the base and the emitter, we have that resistance R pi. And this is the correct polarity for the voltage V pi. Between the emitter and the collector terminal, we have that resistance RE. Between the emitter and the collector terminal, we have a resistance R naught. And between the emitter and the collector terminal, we have our dependent current source. And I argue that the current should be flowing up from the collector to the emitter node. And here we have GM V pi. So let's start here. Does everybody agree that the circuit that I've drawn down on the bottom is the exact same thing as that ugly looking circuit I draw, starting with the small signal model for the BJ2? Anything different? Are any of my voltages defined incorrectly? Are any of my components put in the wrong place or anything like that? Yeah, all right, everything should be pretty legit here. Okay. So there are two different ways that we can approach this, and we'll get the same answer. I'm going to use the easier way, and then if you guys don't believe me, we can work it the other way. So what I'm going to do is I'm going to perform a source transformation, because I have a current source in parallel with two resistances. So I can convert that into a voltage source in series with a single resistance, right? Does not matter that that current source is a dependent current source whatsoever, okay? So if I do a source transformation, what my circuit is going to look like is this. So here's R pi, here is V pi, and I'm free to do this as long as I don't move this particular resistor, because that's where the dependency comes from. In series with this guy, I'm going to see a new resistance, which is RE multiplied by R naught divided by RE plus R naught, because that's my two resistors that are in parallel with my current source. And source transformation lets me put a voltage source in series with that resistance. So this is going to be GM V pi times RE R naught over RE plus R naught. Everybody okay with my application of a source transformation operation? Nothing seems okay. All right, so if I write a Kirchhoff voltage law loop around this equation, I can see that Vx is equal to R pi times Ix plus RE R naught over RE plus R naught times Ix plus GM V pi, where V pi is R pi Ix times RE R naught over RE plus R naught. I'm going to pull out my common factor of Ix. That leaves me with R pi plus RE R naught, RE plus R naught, plus GM R pi, RE R naught over RE plus R naught. And I'm going to notice something real quick here. R pi, by definition, is beta over GM, which means whenever I see GM multiplied by R pi, that is the exact same thing as beta. So using that, I have Ix times R pi plus 1 plus, sorry, beta RE R naught over RE plus R naught, which means my input resistance Rn, Vx over Ix is R pi plus 1 plus beta Re R naught over Re plus R naught. Yep, there we go. So let's start with something easy. How difficult was that? Yeah, so the redrawing here is extraordinarily helpful. After that, it becomes, in my opinion, pretty simple DC circuit analysis. Nothing, maybe a slight step further than what we asked you to do way back in Circuits 1. So nothing wildly difficult here, okay? So I just want to be clear about what we did, because while the answer isn't going to look like this every single time, the methodology is what's important here. So I applied a test voltage Vx across the input terminals of my amplifier circuit, and I'm trying to figure out what the current is that's leaving that test source, okay? I turned off all of my DC voltage sources, which is why my collector is connected to ground, right? I'm looking at a small signal model. So if I turn off VCC, that means I'm short circuiting that voltage to ground. So I'm applying the test voltage here at Vin, which you can't see my finger. I'm turning off VCC and then looking in through those terminals using a specific voltage, measuring the current, and then taking that ratio, okay? So I want to be real clear about what we're doing because we would do the exact same steps. Cameron, what's up? Yes, Vn is the exact same thing as Vx in this case. So that's why I'm applying Vx at that input terminal, right? So Vn in this case is Vx because Vx is placed between the base pin and ground, which is what this implies. So this voltage Vn is a voltage with respect to ground. So we clear on how we do that portion. All right, so if we want to measure the output impedance, it's very similar. So let's say that I have a generic black box amplifier again. What I'm going to do is I'm going to short circuit the input terminals. So let me make a note of that. Get back to those notes. Okay. Then I am going to apply my test voltage across the output terminals and measure the current flowing in, where my output resistance is defined as R out is equal to Vx divided by Ix. So extraordinarily similar, but I have to make sure that I'm shorting my input terminals, and then I'm looking in through the output. So let's do the exact same circuit. Let's find the output resistance of that common collector. Amplifier, all right. With the early effect present. All right, so start with my small signal model. V pi, R pi, V pi. Because early effect is present, I have that guy. Here's my collector, C. Here's my resistance, RE. And then this node right here that I'm circling in real dark is my ground because I ran out of room on this page thing. All right, so my collector, if we look back up here, my collector is still connected to VCC even when I'm looking at it from the output. So that means my collector should be shorted to ground, and my base, which is my input terminal, also needs to be shorted to ground. So let me ask you guys, let's scroll up here real quick. Where in this circuit do I apply my test voltage? At V out. So V out is the voltage drop, is the same thing as the voltage drop over that resistor RE, right? So I'm just going to put a voltage source in parallel with that resistor RE. So here is Vx, and here is my current of interest, Ix. And there's another situation where redrawing things is going to make this a lot easier to determine what's going on. So here's my voltage Vx, here's my current Ix. This is my emitter. Down here is both my base and collector terminals because they're shorted together. So in parallel with that, I see RE. R not. R pi, where this is the polarity of V pi. And finally, my current source. So let's just make sure we've redrawn things correctly. So I'm saying that between node E which is right here, and nodes B and C, which is this guy I've outlined in blue, I have my voltage source, my resistance RE, my resistance R pi, my resistance R naught, and then that current source where the current is flowing from the collector node to the emitter node. So have I redrawn it correctly? Yeah. All right. Just want to be real clear about how I'm redrawing things. So in this case, I'm just going to use Kirchhoff's current law to figure out what Ix is in terms of Vx. So for instance, I could say that Ix is Vx divided by Re plus Vx divided by R naught plus Vx divided by R pi minus Gm times V pi, where V pi is exactly equal to negative Vx. Everybody okay with that? So I'm assuming all my resistor currents are flowing down. And because my dependent source current is flowing up, that's why it gets the negative sign. And I can observe very easily that because all of those elements are in parallel, Vx is exactly the same as negative V pi. So this gives me Ix is equal to Vx multiplied by 1 over Re plus 1 over R naught plus 1 over R pi plus Gm, which means our output resistance Vx over Ix is 1 over Re plus 1 over R naught plus 1 over R pi plus Gm to the minus 1 power. So it looks like 4 resistances in parallel. Anything? Yes, Cameron. Pardon? All right, so I have negative Gm multiplied by negative Vx gives me positive Gm Vx. Then I factored out Vx from everything. All right, so nothing wild or crazy here. All right, because we don't have the time to go through all of them, I'm going to post some notes on calculating the input and output impedance for all 3 different basic amplifiers with and without the early effect online today for you guys. So just as a starting off point for when we get into that portion. All right, so calculating input and output impedance, fairly straightforward. We've established the rules and all that kind of jazz. I've introduced the 3 different types of amplifier circuits. So our next topic, and this one's gonna probably run into the beginning of today's Wednesday, Friday's lecture, is biasing circuitry. All right, so let's specifically start with talking about Npn Bjt Amplifier Biasing. All right. So really, what we're going to be discussing in this section is, I think, 4 different ways total in which we can bias our amplifier circuits under the specific constraint that we need to have the circuit with a DC operating point condition that is in the forward active region, because our BJT needs to be in the forward active region in order to be used as an amplifier. In the saturation, we don't get that amplification that we see. So we're trying to figure out effectively what the rules are for these different schemes to force the circuit to be in the forward active region, or at worst case scenario, soft saturation, where it still behaves roughly like forward active. So let's start with what the textbook calls simple biasing, okay? So a simple biasing scheme looks something like this. And this should arguably be a little bit familiar. And I'm going to define some parameters of interest. IC, IB, our voltage, VBE and our voltage VCE, okay? So the ultimate goal here is to develop the relationships that will allow us to keep VCE greater than VBE in terms of these different circuit parameters, all right? So let's start with something reasonably simple. Using Kirchhoff's current law, Kirchhoff's voltage law, we can see that VCC, the power supply voltage, is equal to our base current IB times our base resistance RB plus our voltage VBE. Anybody got any problems with this? Simple KVL. All right, so we can rewrite this equation and find that our base current IB is simply VCC minus VBE divided by RB, just algebra. And because now we have an expression for our base current, our collector current is just beta IB. So that's going to be beta VCC minus VBE over RB. Now that we have an expression for IC, well, let me stop here. Everybody following along thus far? All right. So now we need to figure out how to relate VCE to these quantities. All right. So if we use KVL again, we can see that VCE is simply VCC minus IC RC, and then substituting in, we get VCC minus beta VCC minus VBE divided by RB times RC. So in order to maintain operation in the forward active region, we know that VCC minus beta VCC minus VBE divided by RB multiplied by RC must be greater than VBE. So we simply have to choose resistor values that causes this to occur. So these are our ground rules for the simple biasing method. So any questions before we kind of put these into practice about where any of this stuff came from or any of that jazz? Cameron. IB times RB would be the voltage drop over that resistor RB, which is not the same as VBE, right? So that would be IB times RB is this voltage drop. Let's call it VRB. And VRB plus VBE must equal to VCC from Kirchhoff's voltage law. All right. How much space? I got good amount of space here. So let's work an example problem here. This is from the textbook. So it says, for the circuit shown below, beta is equal to 100 and IS is equal to 10 to the minus 17 amperes. We are asked to determine the collector current IC and verify that the transistor operates in the forward active region. So we have a 1 kilo ohm resistor there. Let's put a 100 kilo ohm resistor here. Here's 2.5 volts. Here's IC, IB, VBE, and VCE. So how can we solve for any of these quantities, right? So let me think about how to put this. In order to solve for IC, we need to know what VBE is, right? Because IC is IS, EXP, VBE over VT. 100% of the time for a forward active region BJT. So how can we solve for the quantity VBE? So, okay, so look at this equation up top here. All right, and this is, and sorry, what was that? $2.5 minus 100K IB. Yeah, I mean, I'm talking about a numerical value or something like that. So you are correct, but so if we look at this equation up here, and I think the textbook is actually pretty sneaky about the numbers that it uses here. If we set, instead of having greater than there, if we put an equal sign there, what does this imply? Well, so for forward active operation, if we put an equal sign there, that means we're on the edge between forward active and saturation, right? We're saying that VCE greater than or equal to VBE gives us forward active operation. So we have one equation with a single unknown, right? VBE is the only thing that we're dealing with there, but because of the numbers in this problem, let's look at what's happening here, okay? It does turn out that way specifically, right? So we would have 2.5 volts minus 100 times 2.5 volts minus VBE divided by RB, which is 100 kilo ohms, times RC, which is 1 kilo ohm. Let's call it greater than or equal to VBE. So when I have 100 multiplied by 1,000, I get 100,000 kilo ohms in the numerator and 100,000 kilo ohms in the denominator. Does everybody see that? So those guys cancel each other out. Then I have 2.5 volts minus 2.5 volts. So those guys cancel out. I have negative VBE is greater than or equal to, or excuse me, negative VBE is greater than or equal to VBE. So it seems like any value of VBE should work here, but we know that that should not be true, okay? So what we're gonna have to do instead, and it's purely because the numbers make this ambiguous, so we can't use our equation solver on our calculator, is we are going to have to take an initial guess at what value VBE might have based on our experience, and then iterate upon that, all right? So let's label this guy iteration number 1. So we are going to take a shot in the dark and make a guess at what VBE is. So somebody throw me out a number. What was that?
1 volt.
1 volt. All right, let's see what happens. So from this, we know that IC should be beta, which is 100, times 2.5 volts minus 1 volt divided by 100 kiloohms. So what I'm doing specifically here is applying this equation to tell me what IC is, and then we're going to check things out. So let me get my calculator. Here it is. So I have 100 times 2.5 minus the variable I'm storing as X divided by 100 kiloohms. And I'm going to store the results of this as Y. This gives me a current of 1.5 milliamps. All right. Now, for iteration number 2, I'm going to use that value of IC that we just determined based on our guess value for VBE to calculate what specific value of VBE gives us that value of IC. So we know that VBE is equal to VT natural log of IC over IS. So that would be 0.026 volts times the natural log of 1.5 milliamps divided by 10 to the minus 17 amps gives us 848.683 millivolts. So we had a pretty considerable change in VBE, roughly 150 millivolts. So we're probably not there yet. We want to see that change get smaller. We effectively, we're looking for it to settle on some value. So we can use this new VBE to calculate IC. So that would be my new value for X. And so I'm doing the same thing, 100 times 2.5 minus now 848.683 millivolts over 100K gives me 1.651 milliamps. Let's look at iteration number 3. From this, I get 851.181 millivolts with a corresponding IC value of 1.649 milliamps. So at this point, I feel like I'm probably pretty good because it's settled to within 2 microamps. They're about 2 or 3 microamps, yeah. So I feel like further iterations aren't really going to do a whole heck of a lot. So I want to be clear about what I was doing in it, right? I guessed a value for VBE, plugged it into my equation, and solved for IC. Then I used that version of IC to back calculate for VBE, plug that value of VBE back in, calculated for IC again, and repeated over and over until I converged to a final value. This is what your calculator is actually doing when you use that one equation, one unknown solver. It approaches it from the left and from the right, but the reason why it didn't work in this case is because every number is a generic solution based on the way that it was set up. If we had a different beta, that would not be the case. If IS were a different number, it would actually, if we had a different beta, it would change things. Or if we change one of those resistor values, we could have used our calculator initially. But because the numbers in this problem specifically were set up to be a pain in the butt, we had to go through this method. All right, so I just wanted to illustrate it in case that pops up again in your homework. I do not know if it does. I haven't looked at the homework yet. I just wanted to make sure that that was covered. All right, so we have determined what our collector current is. We know it's going to be somewhere pretty dang close to 1.65 milliamps. How do we go about calculating VCE to make sure that this guy is in the forward active region? Right. So VCC minus IC times RC. So let's sneak that in right here. So that would be 2.5 volts minus 1,000 times the variable I have stored as Y. 851.181 millivolts. Does it make sense that VCE and VBE are the same number here? Well, sure. Mathematically, we showed with these numbers, we should see that VCE and VBE are the same thing. We just needed to prove that it doesn't work for every possible value of VBE. So this particular guy is operating at the very edge of the forward active region, between forward active and saturation. All right, so that's one method that can be used to bias transistor amplifier circuits. That being said, it isn't used a whole heck of a lot. And the reasons for this are that as technology progresses, we've been using smaller and smaller values of power supply voltages, okay? And our collector current here, we can see right here, is based heavily on 2 factors, the value of beta and the value of VCC minus VBE. So if we have an unstable power supply, if there's a, if it's a noisy power supply voltage, we are going to see that our collector current is going to swing wildly. And for this particular combination, that could mean that we might hit deep into saturation just based on a little bit of a small ripple in our power supply voltage. Also, because it's based so heavily on beta, beta depends a lot on temperature. And so this guy is going to be very unstable due to temperature fluctuations as well. So the next guy that we're going to introduce tries to rectify a few of these problems. So our next scheme is called Resistive Divider Biasing, okay? So we have, there's our RC. Here's VCC. I'm going to call this guy R1. So this is our simple biasing structure. All I'm doing is adding to it one more resistor, R2. I'm going to define voltage VBE here. Here's a voltage VCE. Here is our collector current IC. So there's two different approaches when we are using resistive divider biasing, okay? The first approach is to say that the base current is effectively negligible in comparison to this current right here. Let me do a different color. Let's do it in green. All right. So if the base current, meaning, let's call this guy IR1, if the base current is negligible, that means we are considering that that current I have labeled as IR1 is roughly the exact same thing as the current I have labeled IR2, which means that our base emitter voltage VBE is pretty trivial to figure out because it's just a simple voltage divider. We're assuming effectively that everything to the right-hand side of our voltage divider doesn't load our voltage divider and cause that output to change, all right? So let's talk about this specifically. Approach number 1, IB is negligible. And let's put a limit on this. So let's say that IB needs to be less than 5% of that current IR2. This is not specified in the book. This is just something that I am adapting because I don't like the lack of specificity here, what's negligible versus what is not. So I'm giving us a criteria that we need to meet. Yes, Mr. Washington. IR2, yes. So that is the current flowing through the voltage divider network. All right. So in this condition, we should see that VBE should be really close to VCC multiplied by R2 divided by R1 plus R2. Simple voltage divider equation, nothing wild or crazy there. Which means IC will be IS times the exponential of VBE over VT, which is the same as IS EXP R2 over R1 plus R2 multiplied by VCC over VT. So let's throw some numbers in here and see what happens. All right. So here's our circuit. Five kilo ohm resistance. $17 kilo ohms here. 8 kilo ohms here. And we want to find, let's see, beta is equal to 100. IS is equal to 10 to the minus 17 amps. Stop doing that. And we want to figure out what IC is. We want to make sure that VCE is greater than VBE, meaning does it operate in the forward active region? And also we want to make sure that our assumption that IB is negligible is true. Because if it isn't, we're gonna have to adapt that, and that's what we're gonna talk about next. All right, so solving this guy is actually fairly straightforward, right? So we can see that IC is 10 to the negative 17 amperes times EXP of 8 kilo ohms over 25 kilo ohms times 2.5 volts over 26 millivolts gives us 230.625 microamps. From this, IB, which is simply 1 over beta IC, is 2.306 microamps. All right. Our current IR2, oh crap. I'll define that here, is simply VCC, which is 2.5 volts, divided by R1 plus R2, 25 kilo ohms, is equal to 100 microamps. So this is approximately 43.4 times our base current, or another way we could do 2.306 divided by 100 is 2.3%, right? So it is definitely what we would consider negligible with that 5% threshold. So that guy checks out. So now we need to check VCC versus VBE. Well, VBE is just determined using voltage division. So that's 2.5 volts times 8 over 25 is, sorry, 2.5, there we go, 0.8 volts. And VCE is VCC minus RC IC, so that's 2.5 minus 5,000 times 230.625 microamps, gives us a voltage of 1.347. So VCE is larger than VBE, so we are indeed operating in the forward active region. Okay. So the last thing that we're going to talk about today is what happens if we can't say that the base current is negligible. How we can approach that. All right. All right, so we are going to approach this circuit now using Thevenin's theorem, or our Thevenin equivalent circuit to our voltage divider network to kind of make things easier. So what I'm really doing here is I'm simply disconnecting this two-port network, or excuse me, two-terminal network. So one terminal is at the base pin of the BJT, and the other terminal is at ground, and I'm going to find the Thevenin equivalent circuit of this, okay? So if I have this network, here's R1, here is R2. This voltage at this pin is my Thevenin voltage. So what's that going to be? Yeah, it is literally governed strictly by the voltage division equation. So V Thevenin should be VCC times R2 over R1 plus R2. All right. Now I also need to find the Thevenin equivalent resistance seen. So remember that finding the Thevenin equivalent resistance means that looking into a dead network, which means that all of our voltage sources are shorted out, turned to zero. So our network is going to look like this. Here's R1, here's R2. We're looking in to that node and we're finding, sorry, not Rn, getting things confused with earlier. R, what did I, oh good Lord, how do I turn that off? I don't like that at all. Hold on just a second. Okay. Sorry about that. So what's the Thevenin resistance seen looking into that terminal? Yeah, because R1 in parallel with R2. So from this, we can say that our original circuit is electrically equivalent to this guy. These represent the exact same things. We're just substituting in that practical voltage source VTH in series with RTH for that voltage divider network. So let's define our current IC, our base current IB, and our voltages VBE and VCE. We got 5 minutes left, so we can develop some equations here real quick. All right. So it should be fairly easy to see that our base emitter voltage, VBE, is equal to our Thevenin voltage minus IB times R Thevenin. And this is going to have to be the same as VT natural log IC over IS, which is the same as VT natural log beta IB over IS. So this guy right here comes from Kirchhoff's voltage law, and these guys come from IC is equal to, sorry, IS that guy. So I'm just being explicit where these guys are coming from so that it's not too confusing. I can rearrange this guy, and I find that IB is equal to V Thevenin minus VT natural log beta IB over IS times the reciprocal or divided by the Thevenin resistance. And this gives me a one equation, one unknown system that I can solve to determine my base current easily for my particular resistor values and things like that. Or my, my parameters, because the Thevenin voltage is dependent on the resistor values, the Thevenin resistance is dependent on the resistor values, and all that kind of jazz. And then from this, I can then say IC is IS times the exponential of VTH minus IB RTH divided by VT, which I'm just substituting in something for VBE there. So I have enough equations to where I can easily either solve directly for IB or do that iterative method if I need it to go back and forth. So we have less than 1 minute left, so I'll work an example using this to start class off on Friday. Okay, so one last thing before I let you guys out of here. Your project is supposed to be due today. There's a thing online that says it's due at midnight and to submit your thing there. So do it. Could you speak up, please? The link, yeah, is up on Moodle. So if you go to Moodle right now, on the thing where it says project number 1, underneath the 2 PDFs, there should be an online submission portal where you can submit. I didn't restrict the number of files, and I did not restrict the file format, so you can send me your schematics and your report, or whatever the hell you want me to grade. I will accept it. Yes.
One per group or one?
Yeah, one per group, please. All right, any other questions or anything? Not see you guys on.
Is the more complicated version work always? I know it's more work.
It's more correct, I guess would be a better way to put it. Yeah. So in my opinion, I don't think it's correct to neglect the base current being 0. So this should give you a more accurate answer every time. Yeah. But technically they're going to be within a couple of % of each other unless the base current is a significant portion of that current IR2. Because what we're saying effectively is that in that original assumption is that, let's find it, almost none of the current splits off, which is likely in a lot of cases.
Well, I just was wondering, because I didn't know if it would be a waste of time to check before moving forward. Or if there was a quick way of looking at it and saying, okay, it's obviously not.
Yeah, I mean, both, to be honest, both equations are pretty straightforward, so I don't know.
Maybe it doesn't matter.
Yeah.
Because we have all this stuff.
So let me stop the recording.